Hi there and welcome to our next lesson in our C5 How Much Quantitative Chemistry lesson. This one is all about indicators and some pH curves. So quite a bit of maths involved in this one because we're going to be looking at some graphs and some interpretations of those graphs. Anyway, I'll see you at the end. Okay, so let's have a look at our objectives for this lesson on indicators and pH curves. So by the end of the lesson, you should know and understand what an indicator is and how they're identified or used to identify the end point of a reaction, and how to construct a pH curve using different strength acids and alkalis. Now we may not cover this in the video, but we will cover this in the practical side of the lesson. Now indicators are chemicals that change colour in acid conditions and in alkaline conditions. Now the ones that you have been used to up till now have been litmus, which comes in a red and blue form, and universal indicator, which comes in a variety of different colours, but you're probably used to it being red in acid and blue or purple in alkali. Now with the universal indicator, you are probably used to seeing this diagram, and this shows the variety of colours that universal indicator will go through at different pHs. So you've got the low pHs, which are strong acid, going to weak acid, and then you've got neutral here at 7, going up to weak alkali, and then you've got the really dark bluey purpley colours, which are your strong alkali. Now last lesson we looked at doing titrations, and we looked at looking for a specific endpoint. Now when we do acid and alkali titrations, universal indicator is not a good example because we've got this range of colours. We can't tell when we hit that neutral point, and we'll see later on when we look at pH curves what sort of range we get with the change in pH. Now ideally you need to use an indicator that will give you a sudden change. So litmus is a really good example, as it goes red or blue when it changes from an acid to an alkali. Other indicators that you can use include phenolphthalein and the one we used last time, which was methyl orange. Now with phenolphthalein in an acid solution, it is colourless, so it's colourless in acid, and then it goes to a red colour when we get an alkali solution. And then with methyl orange, we saw last time that it goes from an orange colour when it's alkali into a pinky colour when it is in acid conditions. Now with titrations, you do have an acid and a base, where you have a solution being either acidified or deacidified, depending on the pH of the solution. Now if you were to have universal indicator as the solution, you'd go through a range of colours in here. So if you were starting with an alkali, oh, don't want that. If you're starting with an alkali, you'd have a purple solution in here. Is that purple? And then that would change to become slightly more blue, and then it would become green, very quickly followed by the yellow, and then we'd end up with a red solution. So you can't really tell when the endpoint of the reaction would be. So you do need to use an indicator like phenolphthalein or methyl orange or litmus, and not universal indicator. Now a pH curve is not what you'd probably expect to find on a graph showing pH. Now you can see here that we've got the pH going here, and then we've got the time going across the bottom. Now if we were to add an alkali to an acid, our pH would start low here, and then what we'd probably expect to happen is it to gradually increase, but sadly that's not the case. Now if we start with acidic conditions, what will happen is as time goes on and we're constantly adding our alkali to it, we would get a very, very small increase until we ended up with our solution changing to becoming alkali. Now we can then use our graph here to work out how much we'd need to add in order to get a pH of 7. Okay, so then we can work out our exact time when it went to neutral. Now if we look here, I'm just going to delete this graph here. We can look at a variety of different graphs that we would expect to have. Now if we had a strong acid with a weak alkali, we would end up with a pH curve that looks like so. Now if we were to have a strong acid with a strong alkali, we would have a pH curve that looks like this. Now again, depending on where you start and what you're adding to it will depend on the shape of the graph that you would have. So I'll delete these two and show weak acid with a weak alkali, and then a weak acid with a strong alkali. Okay, so in the previous lesson we looked at being able to calculate the concentration using the concentration is equal to N, which is the number of moles, divided by V, which is the volume of solution. Now we can put this into our triangle here, so we've got N at the top, C and V at the bottom. So we can work out concentration is equal to N divided by V, and you'll need to be able to use this to work out volume, which would be N divided by C, so number of moles divided by concentration, and to work out N, which will be C times V. Now in a neutralization reaction where it becomes neutral, you will have the same number of moles reacting, so N will be equal to N. So N for the acid will be equal to N number of moles for the alkali. Now if we use the equation that we've just looked at, N is equal to C times V, which will be equal to C times V. So this is for the acid and this is for the alkali. Now what we can do is have a look at an example. Okay, so if 0.025 decimeter cubed of alkali is neutralized by 0.3 decimeter cubed of a 0.1 moles per decimeter cubed of acid, we can work out what the concentration of the alkali is. So if we put in our equations, so C times V is equal to C times V. So we've got the acid on this side and the alkali on this side. We can identify what is what. So the concentration of the acid here is this value here. So we've got 0.1 times by the volume of the acid, which is here, which is 0.03. Now that is equal to the concentration of the alkali, which is what we're trying to work out here. So that is our unknown multiplied by the volume of the alkali, which is here. So that's 0.025. Now what we need to do is we need to make this the subject of the equation. So because this is multiplied, we divide both sides by this. So that will give us a new equation. I'm just going to move this up a wee bit here. This will give us a new equation of 0.1 times 0.03 divided by 0.25, and that will give us a concentration of 0.12 moles per decimeter cubed. Okay, so a quick review of what we have looked at today. We have looked at indicators, the suitable ones that we can use for acid-alkali neutralization reactions, which are phenolphthalein or litmus, or perhaps even methyl orange. We've looked at the reasons why we can't use universal indicator, and we've looked at the interpretation of some pH curved graphs. And just remember that they're like an S for Simon shape at the in the graph. Okay, so you can work out what the neutralization point is, and then you can work out what the concentrations of various acids or alkalis will be. Anyway, I hope you've enjoyed this, and I'll see you next time. Bye bye.